Yeah, it's our pleasure to have Laura here in our seminar to share about her work on improved machine learning algorithms for predicting ground state properties. Yeah, I think it's like Laura, you can start your presentations. Thanks.
Okay. Yeah, thank you for the introduction. Yeah, so I'll be talking today about an improved machine learning algorithm for predicting ground state properties. And this is a joint work with collaborators at Caltech, like Robert Huang and John Preskill, along with also collaborators in Austria, like Via Tran, Sebastian Lenner, and Richard Kuhn. Okay, so to give some motivation for why we care about studying this, as you all probably know, finding ground states is a really fundamental problem in physics. And however, despite much research going into how classical computers might solve this, they still struggle to solve this problem in general. So, for example, one algorithm that's known is the density matrix renormalization group, DMRG. And for one dimension, DMRG is pretty efficient, but for higher dimensions, this problem is very hard and it becomes less efficient. So this leads to then the question of, can classical machine learning efficiently predict ground states after learning from some amount of training data? So does this training data, which functions as like a set of examples given to the algorithm, does that somehow make the problem easier in a way? And last year, Robert, along with collaborators, showed that this is true. So indeed, there does exist a polynomial time classical machine learning algorithm that can achieve this average prediction error of less than epsilon using a polynomial amount of training data for a fixed average prediction error epsilon. So in particular, the training data here scales as n, where n is the system size, so n to the order 1 over epsilon. However, one thing that you might notice is that for a very small fixed epsilon, which is what we want our prediction error to be very small, then this amount of training data, this n to the order 1 over epsilon, is a really, really big polynomial. So the central question of this work is then, can we do better than this n to the order 1 over epsilon amount of scaling? Even though this is, yeah, theoretically efficient for a fixed epsilon, it's only polynomial, then, yeah, is there something that we can do better so that we can get an actual advantage in practice? And in this work, we show the following theorem. So given only logarithmic in n times 2 to the polylog 1 over epsilon amount of trained data, then we can achieve the same average prediction error of less than epsilon. And moreover, there is an additional improvement over the previous work. So the training data can be sampled from any arbitrary distribution. So here I denote that arbitrary distribution as D. As opposed to in the previous work, if you may have noticed, then the trained data can only be sampled from a uniform distribution. So this is another improvement over the previous algorithm. And moreover, we show following computational hardness. So this is really just a corollary of the previous work. But what it says is that assuming that RP is not equal to NP, so this is a fairly standard complexity theoretic assumption, then for two-dimensional Hamiltonians, even just 2 dimensions, then there doesn't exist a randomized classical algorithm that doesn't learn from data, so not a machine learning algorithm, that can predict even one-body observables with an average prediction error less than, say, 1 over 4 within polynomial time. So what this is really saying is that for any classical algorithm that isn't a machine learning algorithm, then this problem is fairly hard, even just for 2D Hamiltonians predicting one-body observables. But meanwhile, this algorithm that we propose works for any Hamiltonian of constant dimension and for any few-body observable. So for an outline of the rest of the talk, I'll go over the problem statement in particular, and I'll give a sketch of the machine learning algorithm and talk more about the main result and the ideas behind the proof, which will hopefully motivate the algorithm more. And finally, I'll talk about some numerical experiments. Okay, so let's talk about the problem. So in this, we consider a Hamiltonian, h of x, which is on n qubits, and we assume that it's geometrically local and gapped. And so this h of x here just means that the Hamiltonian is parameterized smoothly by some vector x, and that vector has to have entries between -1 and 1. And moreover, we have that h of x can be written as a sum of few body interaction terms. And so up until now, these are the same assumptions as in the previous work, but the previous work actually did show that there's a sample complexity lower bound using only these assumptions. And so in order to get our improved scaling of the sample complexity, in order to overcome this lower bound, then we had to add a small additional assumption on the structure of the Hamiltonian, but it's a fairly natural one, and it's as follows. So here we're writing h of x as the sum of these few body interaction terms, these h sub j. But the additional assumption is that these hj depend on this vector xj. And what xj is it's just a constant subset of the entire parameter vector x. So in particular, each of these local terms only depend on a constant subset of the parameter vector. They don't depend on this entire long m-dimensional vector x, but just a constant number of those parameters are what matter. And what we want is we want to make a classical machine learning algorithm where we input the parameters describing this Hamiltonian. So this is the vector x here. And we input that into our machine learning algorithm, and it predicts and it outputs this classical representation of the ground state, or in particular, what we care about is a ground state property. And what I mean by a ground state property is this trace O rho of x, where rho of x is the ground state of the Hamiltonian h of x, and O is a sum of geometrically local observables with spectral norm bounded by 1. And I'll explain later why we need the spectral norm bounded by 1, but it'll come up in the proof ideas. Okay, so this is what we want. We want this ground state property. I've just put the goal up here again. And remember that this is a machine learning algorithm, so we're given some amount of training data. And this training data is of the following form. So it's these pairs XL and YL, and there are a capital N of these pairs. So that's what the sample complexity is, the amount of training data. And the XL just corresponds to some parameters for a Hamiltonian. And so these XL in particular can be sampled from any arbitrary distribution D, like I was mentioning before. And the YLs, the corresponding labels of the training data, just need to approximate the ground state property corresponding to the Hamiltonian with parameters XL. So this is the training data. And there are different ways that you can generate this training data in practice. So for example, you can synthesize a ground state in the lab and then perform a bunch of measurements and be able to create these pairs. Another way that you might be able to do it is by running simulations. So you can use DMRG to generate the training data. Okay, so now I'll talk about the algorithm a bit. And so a really key part of the algorithm is a feature mapping, which I'll call phi, which takes the parameter space and maps it into a higher dimensional vector space. So here this m sub phi is just indicating that higher dimensional vector space. And it works as follows. So suppose that we have our parameters describing our Hamiltonian again. And I mentioned that each of these local terms of the Hamiltonian, each of those hj, depends on only a constant subset of the parameters. So for each local term in the Hamiltonian, you can imagine that each constant region of parameters is really what matters. So I'll just circle each of these little constant regions of parameters. And what we do in the feature mapping, I'm just giving it at the high level, and then I'll talk about what it is specifically in the proof ideas. But what we do is essentially for each of these local regions of parameters, we just create this small vector for each of those regions, and then we concatenate that together for all of the regions. And that's how we get our feature vector phi. And so, like I said, so first we take the parameter space and map it into this higher dimensional feature space created by these concatenated vectors. And what happens is the classical ML model then can learn functions of this form. So here I'm denoting the hypothesis function as h of x. And this w is a vector of coefficients that we learn. And the phi of x, remember that phi is just this feature mapping. And so we can easily learn functions of that form just using standard machine learning tools. So in particular, we use L1 regularized regression or lasso over the feature space. And just as a recap of what I was saying, so overall, the ML algorithm does the following. It takes as input these parameters, and then it runs through generating this feature vector by considering each of these local terms. And once it has the feature vector, then it can just use lasso and output our ground state property. Okay, so like I said, this was a fairly high level sketch of what was going on. So now I'll take some time to discuss the main result in more detail and talk about the proof ideas. Okay, so remember this is our theorem. And remember that the best previously known algorithm for this task has a sample complexity that scales as n to the order 1 over epsilon, where n is again the system size. But here, let's just compare them. Notice that for a fixed epsilon, so for a fixed small epsilon, and like I mentioned before the previous work, then this scales, the sample complexity scales is a very large polynomial. And meanwhile, for a fixed epsilon, then the sample complexity of our algorithm just scales logarithmically in n. So that's an exponential improvement in the scaling and system size for this sample complexity. And meanwhile, if we also include this scaling in 1 over epsilon, then the previous sample complexity was exponential in 1 over epsilon. And meanwhile, ours is 2 to the polylog 1 over epsilon, which is quasi-polynomial. And as I mentioned before, the other small improvement that we have is that the training data can be sampled from any arbitrary distribution D, whereas before it could only be sampled from uniform. And moreover, both of these algorithms require computational time that scales as order a small n, so system size, times the capital N, the sample complexity. And so by decreasing the amount of sample complexity that we need, then we automatically get an improvement in computational time as well. So again, just to emphasize this, for an epsilon that's small and fixed, then the computational time for our algorithm scales as n-logn. And meanwhile, for the best previously known algorithm, then this scales as a very high degree polynomial.
Sorry, Rola, can I ask a question here? Just
Yes.
to clarify something. Yeah, you kind of like emphasized that your algorithm works for arbitrary distributions while the previous one only works for uniform distribution, right? Why does this matter though? As in, will it improve the accuracies, or like what? Under what condition that we should choose the distribution other than the uniform distribution?
Yeah, I guess you could think of it as if if you're only able to say like generate in the lab certain Hamiltonians, or like it could be easier to generate some, then you don't want to have to go and pick these parameters like uniformly, but maybe you can just like cluster around a certain few or something like this. Mainly when generating the training data, then you could run into situations where you want to just use an arbitrary distribution instead of uniform.
Right. Okay. But for example, if I consider like let's say multi-dimensional Gaussian distributions, then would it make a prediction well that if the data points is like far away from the like center of the distributions?
Yeah, it would still,
Okay, let's see. Thanks.
Okay, so this is the guarantee. Okay, so I'll talk about how we prove this theorem. So this is our main result. And it follows by three key parts. And the first is finding a simpler form for the ground state property. And so this is something that couldn't be done in the previous case, and it's really, or by the previous work, and it really comes from this additional structure that we have on the Hamiltonian. So in particular, what I mean by this simpler form is the following. So the ground state property that we want to predict can be approximated by a linear function on the feature space. So in particular, this trace O rho of x that we had can be approximated by some vector of coefficients that I'll call W prime, dotted with the feature vector phi of x. And what this really says is that the machine learning algorithm, remember that when we were running lasso as this last step, then the lasso algorithm would would learn functions of this form. So what this is saying is that the ML algorithm does have the representation power in order to be able to predict functions that we want, or learn functions that relate to this ground state property that we want. Okay, so how do we show that this is true? So first what we do is we show that trace O rho of x can be approximated by some function, f of x, where f is just a sum of smooth functions. And I'll go through explicitly what it is. Okay, and to see what smooth functions it's actually the sum of, the way that we can see this is if we write our observable O in the Pauli basis. So we're just writing it over as a sum over the Paulis of these alpha p's of the Pauli coefficients times p. And then what we can see is that it suffices then to show that alpha p times trace p rho of x is approximated by some smooth function, some smooth local function fp of x. The reason why it suffices to show this is if we sum both sides then over all of these Paulis, then what we get just by the definition of this O is that on the left-hand side, we have the sum of these alpha p, p, and so that's just O. So on the left-hand side, we have the trace O rho of x. And on the right-hand side, we, like I said, because the fp are smooth functions, then we just have a sum of smooth functions. So in particular, the sum over these Paulis of fp of x is just the function f. That's how we define it. And so I mentioned that these fp of x are local in a certain sense. And what I mean by that is that these fp of x are really, really close to the ground state property we want to predict. So they're almost this alpha p trace p rho of x, but not quite. So they're this row of chi p of x. And what I mean by this chi p is that it denotes parameters, the parameter vector, with parameters that are quote unquote far from p set to 0. Okay, so essentially the idea of what this is saying is that only parameters that are close by to p matter for this ground state property. And this kind of matches up with what I was saying before about how a local term in the Hamiltonian, like these hj, depend on a constant subset of parameters. And so this constant region is what matters. And that's really similar to what I'm saying here. But let me say precisely what I mean by this like far from p. So what I mean by this is, suppose we have one of these local terms of the Hamiltonian. We have this hj that acts on qubits, say, that are far away from the qubits that the Pauli p acts on. And then we need to consider the parameters that hj depends on. So these are the parameters that we say are far from p. So just to say it again, parameters are far from p if some local term hj depends on them, and the hj acts on qubits that are far from the qubits that p acts on. Say if we considered laying out the qubits on like a 2D lattice or something. So in that terms of distance, I mean, for the qubits being far. Yeah, and so this is kind of a mouthful to say every time I want to say it. So that's why I just do this quote unquote far from p, okay? So that's what I mean for the rest of the talk whenever I say this. Okay, and again, just to emphasize, what I said before. So this fp of x is, yeah, local sort of function. And what it's saying is that we can essentially throw away all of the parameters that are far away from p. They don't matter, we're just setting them to 0. And the only things that matter are these parameters that are close by. And those are the only things that contribute to the ground state property. So I've just put what I set up here as a lemma. So here, this FP is exactly how I defined it before. And I claim that this approximates the alpha p trace p rho of x. So the actual ground state property we want to predict is approximated by these local functions. And the way that we show this is, like I said before, only parameters that are close to p affect the ground state property. And show that, we use two main tools. One is the spectral flow formalism, and the other is Lieb-Robinson bounds. So you might remember in the spectral flow formalism that the main result is that they bound the directional derivative of a ground state. And what we show then is that we show that when we change coordinates far from p, so if we take the directional derivative along a certain direction that changes one of these parameters that are far away from p, we're trying to change it to 0. So when we take the directional derivative in that direction, we can use the spectral flow formalism to bound this directional derivative. And we can show that this doesn't change it much. And in the process, we need to use some Lieb-Robinson bounds as well to bound the integrals. And so this is essentially how we get this lemma, which is really a key part of the work. Okay, and from that, how do we obtain this theorem? So remember that the previous lemma actually showed that trace O rho of x was approximated by f of x, where f of x is the sum of these fp for all the Pauli's p. And so we want to go from that claim to this one, that the trace O rho of x can actually be approximated by this linear function over the feature space, instead of this sum of smooth functions. And the way that we do this is we discretize the input space of each local function, fp. So for a sufficiently fine lattice over this input space, then if we replace x by its nearest lattice point, we can show, using the smoothness of these fp functions, that this causes a small amount of error. And so what I mean by replacing x by its nearest lattice point will become clear when I mention this feature mapping. So the feature mapping phi of x is just exactly what I mean when I say like the replacing x by its nearest lattice point. So in particular, this feature mapping is really just a vector of zeros and ones, and each entry of the vector corresponds to one of these lattice points. And the entry is 1 when x is close to the lattice point. So essentially this phi of x, you can just think of it as like a vector where each of the entries are indicator functions for checking if x is close to a lattice point. And then the coefficient vector just contains, again, entries where each entry corresponds to a lattice point. And we evaluate fp on each of those lattice points. And then you concatenate those over all of the different Pauli's. So the key here is really, this discretization technique and replacing x by its nearest lattice point. And that's really all that we do here. So this is a fairly short part of the proof. Okay. And when we do that, then we obtain the theorem that we wanted. So just to bring this back to kind of what I was saying about the machine learning algorithm before, remember that this represents the parameters of the Hamiltonian. And so for each of these Pauli's p, then we kind of have a region, and it's approximated by a linear function of this vector. for each of these smaller vectors. And so if we concatenate this larger vector together, we can still obtain this linear function. Okay. Yeah, so maybe I can say it a bit more precisely. So for each Pauli term P that's close to some local term of the Hamiltonian, we only really need to consider those parameters corresponding to the local term when we predict this ground state property. And that was the ground state property I mentioned about the alpha P trace P rho of X. And so for each Pauli, you only need to consider one of the regions like I had before, and we create a small vector for that region. And for that ground state property, that alpha P trace P rho of X, that's approximated by a linear function of this vector. Okay, because this is the kind of the feature vector for that specific Pauli. And then adding all of the Paulis together, concatenating all of these smaller vectors together, then that's how we get the linear function. This was the general idea. And again, what we obtain by this theorem is that the ML model has sufficiently high representation power to cover this ground state property. And this is really the main part of the proof, in my opinion. But we do need two other different parts. And one of them is this norm inequality. So you may be familiar with that the efficiency of L1 regularized regression, which we use, depends greatly on the L1 norm of the coefficient vector W. So in particular, remember that in the lasso algorithm, then there's this hyperparameter that we need to set that corresponds to a constraint that we optimize with respect to. So in particular, this constraint is some B such that the one norm of the vector of coefficients, W, is bounded by B. And so how do we choose that hyperparameter B? Well, we can choose it based on W prime from the previous slide. And while the ML algorithm may not learn the specific vector of coefficients, that W prime, then even still, by asserting that the one norm of W in lasso, must be less than B, then this guarantees that whichever W star, say, which could be, very different from W prime, whichever W star that lasso finds will yield an even smaller training error. Okay, yeah, so that's how we choose this B. Okay, by looking at the one norm of W prime, because we have an explicit form for that from the previous slide. Remember that it was like this vector where we evaluate the FP on each of these lattice points. So we have an explicit form for that, and we can bound the one norm. But what we really need in order to bound the one norm is this additional inequality. And so it's fairly simple to state. What it says is that we write the observable O in the Pauli basis again. And here I'm just using Q instead of P. And it's the same thing. So we have an observable O that can be written as a sum of geometrically local observables. And what we have is that the sum of the Pauli coefficients, the L1 norm of the Pauli coefficients, is bounded above by some constant, C, times the spectral norm of O. And this is why I said I would point this out. This is why we require that the spectral norm of O be bounded by 1. Okay, because we want this one norm of the Pauli coefficients to just be a constant. And so this is just a norm inequality that we need in order to bound the one norm of W prime, just something we need along the way. And we expect this will be useful as well in other learning techniques, because often we do care about, say, the L1 norm of different coefficients. Okay, so I've just stated the theorem again, but I'll provide a brief sketch of how we do this. So to prove this, you may recall that for a quantum state rho, then trace O of rho is bounded above by the spectral norm of O. And so in order to prove this norm inequality, then it suffices to find some test state rho such that the one norm of the Pauli coefficients of the observable O is bounded above by C times this trace O rho. And what we do in the proof is we exactly find such a test state rho. And it's a bit of a complicated construction or complicated to formalize. So but I won't say too much more about it, but you can feel free to look at the paper for that. Okay, and the last part of the proof is just putting everything together. So it's just this prediction error bound. And what we do in this is, just to summarize, so in the first part of the proof, I showed that there's a simpler form for the ground state property, which guarantees the existence of a hypothesis function with low training error. So the simpler form was, remember, this linear function over the feature space. And using the norm inequality, what we know is that the sum of the one norm of the Pauli coefficients is just a constant. And so then we can choose B, this hyperparameter B that we use in lasso. We can set that just so that it bounds the one norm of W prime above. And it turns out this B is to the order polylog 1 over epsilon. So when we run lasso with respect to this constraint that the one norm of these coefficient vectors has to be bounded above by B, then just some really standard learning theory about the prediction error of lasso gives the sample complexity upper bound. So from here, we really just need to plug in B, and we plug in the rest of our parameters into this theorem. And then we can just solve for the sample complexity. And this is also how we get that the training data can be sampled from any arbitrary distribution, because this standard learning theory result doesn't have any restrictions on this input distribution. Okay, so again, here's the theorem. And once again, as I've said many times, I want to emphasize the improved scaling. So previously, again, for fixed epsilon, then scaling in n, and the previous result was a very high degree polynomial in n, but here it's only logarithmic. So this exponential improvement, which we expect to help in practice. And so in particular, talk about the in practice part, I'll talk about some of the numerical experiments that we ran. So in these experiments, we consider the 2D random Heisenberg model. So we just have these spins placed on a two-dimensional lattice. And the Hamiltonian is a familiar one. And so the sum here is just over all nearest neighbor pairs of qubits, I and j. And this Jij, they're the coupling parameters. And so to put this back into the framework of the ML algorithm, what we have is this parameter vector x is just all of these Jij. And in this, we care about predicting two-body correlation functions, so the expectation value of these for each pair of qubits I and j. Okay, and here are some of the numerical results. So I'll go through each of them. So in all of these top figures, let's look at those first. Then the gray lines indicate what was just the numerical experiments on the previous work. We just reran them. And yeah, so all three of those were what was done in Robert's previous work. And the blue line is our algorithm being run, our new algorithm. And one thing that we see, so in this left and center figure, we see that this emphasizes the improvement on scaling in terms of epsilon. So why is that? So we can see this is on the x-axis of the leftmost figure, this is the measurements per system. So in particular, it's the classical shadow size. And we have the average prediction error on the y-axis. And here we have the training set size on the x-axis, and again, average prediction error on the y. And what we see is that here, as the measurement per system size, so the classical shadow size increases, or as the training set size increases, then the average prediction error drops at a much higher rate. Okay, and yeah, so this shows the improved scaling in terms of epsilon of the training set size. And in this rightmost figure, again, we have the three lines comparing to previous work. And we see here that as system size increases, it's a really good sign that the average prediction error doesn't increase too much. Okay, and that emphasizes the logarithmic in n scaling that we had for the sample complexity. And I guess we can point out here that in the previous work, this kind of trend also showed up, that as system size increases, then average prediction error didn't drastically increase. But in the previous work, this wasn't theoretically justified at all, right? Because before it was this very, very large polynomial, the sample complexity. And so, yeah, before it wasn't theoretically justified, but here we can see a reflection of our theory here. And in the bottom part, so these are really just visualizations. They're all essentially the same, just for different pairs of qubits. But what this is saying is just that. So for each pair of qubits, so I've just written the 2D lattice for the 5x5 system. And the thickness and darkness of each of the lines between the qubits indicates how much that coupling parameter affected the machine learning model, like how high it was weighted in the final model once it was trained. And this really reflects the local nature of our function, of our machine learning model. So here we have for qubits 4 and 5. So we're predicting the two-body correlation function between the qubits 4 and 5. Then, as you might expect, then the coupling parameter between those qubits 4 and 5 in the Hamiltonian was the one that mattered the most. Okay, so it's the thickest and the darkest line. And meanwhile, for qubits that are kind of nearby, then we see that they also played a factor in the machine learning model. But as you get further and further out, then those really don't matter at all. In fact, I think all of these coefficients were just 0, and we just drew them in lightly to just denote them. But yeah, we see that only this local region matters. And so that really does emphasize this local nature of the model that I was talking about in the proof ideas. And we see similarly for the other qubits. So this is just repeated for different pairs of qubits. So here we have between qubits 6 and 11. Again, the coupling parameter between qubits 6 and 11 is the one that matters most, and similarly for qubits 18 and 19. And now I can conclude. So in conclusion, we proved that these classical machine learning algorithms can predict ground state properties, which much less data than was previously known. And this really raises the hope that we can actually use ML in practice to be able to do this, because oftentimes in the real world with physical experiments or just running DMRG, it might be very expensive to actually obtain a lot of data. So given this only small amount of data that we can gain in the real world, we might actually be able to use ML for this in practice. I'd like to mention some of the open questions. So one open question that we have is, can quantum ML algorithms predict ground state properties even better? So here, these were just classical algorithms, classical ML. But yeah, if we were to try to do something in quantum, yeah, would this gain any sort of advantage? And another open question that we have is, can ML learn to predict some other physical properties? So for example, like low energy states instead of ground state properties or things like this. And yeah, that's all I have for this talk.
Yeah, thanks, Rola, for the very interesting talk. And your work once emphasized again that the importance of constructing a right feature maps for for some machine learning models in order to learn the physical properties of quantum system. Yeah. So now if the audience have any questions, you can either unmute yourself or just raise your hand. I'll type the question in the chat. Elias, we have a question, so maybe you can unmute yourself and ask questions.
Sure, yeah. Actually, I have a question just on the the encoding part. So all the theoretical guarantees are like given this feature map theta, right? So my question is, in the example, in the numerical example you showed, it was very straightforward to construct this map, but it also depends on the form of the Hamiltonian. So like, do you have any results or like any insights on how hard it could be to generate, like to calculate, to find the form of this feature map in the first place? Whether this itself might be a hard problem for certain types of Hamiltonians.
Yeah, that's a really good point. So actually for the numerical experiments, then we didn't use this feature mapping. So the reason the feature mapping is essentially, this vector of like zeros and ones. But in practice, this can be, pretty hard to actually compute because it requires discretizing this like big input space. And for high dimensions, that can be a really hard problem. And so what we did in practice for the numerical experiments was we did it with a random Fourier feature. And so that's something that's, more commonly used in like practical machine learning. It doesn't have any theoretical guarantees, but it still works fine in practice. Yeah, and it's also much more robust than our like zeros and ones vector for the feature mapping. That was really just a tool to make the proofs go through.
Makes sense. Thanks.
Yeah, while other people think of the question to ask, maybe I could ask one question. I remember in Robert papers, basically, they consider the Rydberg atoms, as the Hamiltonians, and use the predictions of the ground state property over there. But in their system, basically, they also kind of like try to see the predictions on like different phases of that. Would your algorithms also be able to kind of predict the ground state properties like for different phases of the Hamiltonians?
Or do you mean like predicting ground state properties for different like phases of matter, like across different phases of matter?
Yeah.
Yeah, we haven't tried it, but I expect since the previous algorithm did work for it as well in practice, then yeah, I would expect that this one would also work in practice. But just like theirs, we don't have a guarantee on, like a theoretical guarantee on doing that sort of algorithm. But yeah, in practice, it would probably work.
Yeah, I think it's like for the previous algorithm, they also didn't really have a plural guarantees on that.
Yeah.
Right? They just like run numerics and show that it works. Yeah. So like for this, I think like you consider square lattice for simplicities, right? In general, it works for arbitrary like shape of the lattice. Then you can construct like feature maps using the same methods and make the predictions, right?
Yeah.
Okay. Right. Yeah, as in like for your as in this is quite general, and maybe it is I suppose this should be an open question as well. Like in your papers and Robert papers, basically you guys like consider the static Hamiltonian, like it doesn't like depends on any like time. And say now if you have like driven Hamiltonian systems, then how like would you expect your algorithms still work for this kind of system? Because like when you have like driven many-body system, then there will be some, for example, thermalization phases or like many-body localization phases like occurs in the systems, and then the correlations between the qubits might spread around after when you evolve the system for quite some time. Yeah, in this case, like how your algorithm be affected by this like additional driven kind of like term in Hamiltonian.
Yeah, I'm not really sure. Yeah, I think that's still an open question.
Right, sure. Yeah, so currently I didn't see any question from the audience. Maybe they just need some time to think of the questions to ask, and maybe they'll like kind of like email you the questions when they're not out one. Yeah, I think we can like should be able to end the seminar here. And thanks Laura again for the very interesting talk. and looking forward to have you in the futures. And yeah, see you all. Bye.
Yep. Thank you.
Thank you.